we are going to see a problem based on continuous time Fourier series. So here is the problem. The problem is like this. Determine the trigonometric form of Fourier series of the waveform shown below. So the waveform is given like this. So the time interval over here is t by 2, this is t minus t by 2 minus t. So this is a waveform given, and for this we need to find out trigonometric form of Fourier series. So before writing any equation and applying to this particular waveform, we need to first find out the time period of the waveform. So time period means what? The time taken by a waveform to complete one part or one cycle. So over here it is very important to decide what is the cycle. So if you see properly, this part of the waveform is a cycle. Because if I take this part and join over here, I will get a waveform in a continuous manner. So I will consider this is a one cycle. And this one cycle is getting completed in t time. So I will consider time period as capital T. Now only this particular waveform we need to find out for a application of a Fourier series. So now I will take this cycle aside. I will get like this. Why this is required? Because now waveform we are going to convert into equation. So it will be like this. X of t equal to a constant capital A. This is for the time interval 0 to t by 2. So A is from 0 to t by 2 like this. And then t by 2 to t, it is minus A. So now I can say this x of t is in time interval from 0 to t with time period capital T. What is the use of this capital T? Now, in our formula we have a omega. So omega is 2 pi divided by time period. And since the time period over here is now capital T, so I can say omega is 2 pi by T. So wherever omega is there, we will replace it with a 2 pi by T. In the end, if I multiply, I will get omega T as 2 pi. So sometimes we deal with omega T. So omega T is 2 pi in this case, that we have to keep in mind. Now all the background work is ready now. Let's proceed further to writing a Fourier series representation of x of t. So x of t can be represented like this. A DC term a0 plus summation n from 1 to infinity, and we have an cos n omega, or you can consider omega 0 is nothing but a fundamental frequency. So whatever we have calculated over here is nothing but a fundamental frequency only. So I will consider it as n omega t plus bn sine n omega t. So our job is to get a0, an and bn, which is given by a0 is 1 upon time period, and over here the time period is capital T. So it's a 1 upon t. Waveform exists from 0 to t. So 0 to t, x of t dt. This can be solved like this: 1 by t. Since the waveform is defined in two intervals, 0 to t by 2 and t by 2 to t, so I will write this equal to 1 by t in bracket 0 to t by 2 is the first interval, and in that interval waveform is having a value capital A, and remaining interval t by 2 to t, the waveform is having a value minus A. So if we solve this integral, we will get A by t integral of this is t, limits are 0 to t by 2. Same way, here also if I take a common, this minus will come, and integral of dt is t, and the limits are t by 2 to t. So let's apply the limit. So a0 will be a by capital T, t by 2 minus 0 minus t minus t by 2. So after solving, we will get a0 as a upon capital T in bracket t by 2 minus, if I solve this, this will be t by 2 these two getting cancelled. So in the end, we will get A0 as 0. So the constant term in the Fourier series of x of t will be 0. Let's find out the an. So an is given by 1 upon half the time period. Waveform exists from 0 to t, x of t cos n omega t dt. So since waveform has two parts, hence this integral will get split into two like this. Zero to t by 2, it is having a value a, and t by 2 to t, it is minus a. So if we simplify, a get common, so it is 2a upon capital T in bracket integral 0 to t by 2 cos n omega t dt minus integral t by 2 to t cos n omega t dt. Integration of cos is sine, so we'll get sine n omega t divided by derivative of this term with respect to t, which is n omega, and the limits are 0 to t by 2. Same way over here also, sine n omega t divided by n omega, limits are from t by 2 to t. So if you apply the limits, before that, let's take this n omega common. So it is 2a upon t into n omega inside a bracket. If I apply the limit, it will be sine n omega t by 2 minus, over here it is 0, so sine 0, this will come in one bracket, minus in second bracket it will be sine n omega capital T minus sine n omega capital T by 2. Now this we will get, and over here we know sine 0 is 0. Moreover, in the first step we have calculated omega t is 2 pi. So let's substitute wherever we are finding omega t, and we substitute that as 2 pi. So here I am having omega t, omega t, omega t. So that need to be substituted with 2 pi. So after doing so, we will get an as (2a) divided by omega t into n. In fact, here also we can substitute, but that will substitute in the next step. We will get sine n by 2 into 2 pi, and sine 0 is 0. And let's open up this bracket with this negative sign by changing signs of all the terms. So it is minus sine n into 2 pi plus sine n by 2 into 2 pi. Let's simplify. So I will get an as 2a omega t is 2 pi. Simplify means what? I can cancel 2 over here and here, so that in the end we will get sine n pi minus 0 minus sine 2n pi plus sine n pi. And we know in trigonometry, sine n pi or sine 2n pi is always 0 for n which is any integer. So what we are getting over here, all these terms will be 0. So in the end I can say an will be 2a upon 2 pi n multiplied by 0. So an also we will get as 0. So we got a0 as 0, n also 0. Let's find out a bn now. So bn is 1 upon half the time period integral 0 to t x of t sine n omega t dt. So over here it will be 2 by capital T, integral gets splitted into two limits because x of t is a in 0 to t by 2. And from t by 2 to t it is minus a. A I can take common and out of an integral, so it is 2a upon t inside bracket. We have integral 0 to t by 2 sine n omega t dt minus integral t by 2 to capital T sine n omega t dt. Now 2a by capital T, integral of sine is minus cos divided by derivative of this term which is n omega, and the limits are 0 to t by 2 minus, once again integration of sine is minus cos derivative n omega with limits t by 2 to t. Now we need to apply the limits to this particular equation. Before that, let's simplify by taking this n omega n out of an integral. So it is 2a upon n omega capital T inside a bracket. Let's simplify this. This minus minus will become plus. So let's write this term first. So it will be cos n omega t, limits are t by 2 to t, minus I have taken out in bracket cos n omega t, but limits are 0 to t by 2. So we can apply the limits now. So we'll get bn as 2a upon n into omega t. After applying the limits, we'll get, so after applying the limits, we'll get n omega into capital T minus cos n omega into capital T by 2. minus cos n omega capital T by 2 minus cos 0. Now since we know omega capital T is nothing but 2 pi, so wherever a omega capital T is there, we will replace it with a 2 pi, so that we will get Pn as 2a upon n into 2 pi bracket cos 2 pi n minus cos n by 2 into 2 pi. Let's open this bracket. So minus cos n by 2 into 2 pi, and finally cos 0, which will come as plus cos 0. So now 2 to get cancelled over here, and after simplifying I will get Bn as, in fact we can cancel this 2, so that it is a upon n pi in bracket cos 2 pi n minus, see these two terms are same, so I can add them up and it become minus 2 cos n pi plus cos 0. So from the trigonometry we know cos 0 is 1, cos n pi is minus 1 raised to n, and cos 2 pi n is 1. So let's substitute this. So we'll get Bn as a upon n pi in bracket 1 minus 2 into minus 1 raised to n plus 1. So Pn is a upon n pi bracket 2 minus 2 into minus 1 raised to n. I can take 2 common. So Bn is 2a upon n pi in bracket 1 minus minus 1 raised to n. Now we can make it a specific by putting the values of n. So we know if we put a value of n as an even number, minus 1 raised to that even number will always give you 1. This 1 will get cancelled with this 1, so in the end we will get answer 0. But if I put n as an odd number, 1, 3, 5, minus 1 raised to that odd number will give you a minus 1, 1 minus minus 1 will give you 2 always. So this 2 is getting multiplied with this 2 becomes the answer 4. So what I can do, I can write Bn as 0 and Bn as 4a upon n pi. But I'm getting Bn as 0 if n is even number, meaning 2, 4, 6 likewise. And I'm getting this answer 4a divided by n pi if I have n as odd number, meaning 1, 3, 5 like this. So in the end I can say Bn having this answer. Now we got all the 3 coefficients. Let's list out. We got a0 as 0, we got an also equal to 0, and Bn we got either 0 or 4a upon n pi, and that depends upon the values of n. This is when n is even, and this we obtain if n is odd. Now with respect to this, our x of t having a representation a0 plus summation n from 1 to infinity an cos n omega t plus pn sin n omega t. And if I put all the values in the end, I will get x of t as 0 plus summation n equal to 1 to infinity 0 plus bn. We will write a generalized statement like this. So it is 2a upon n pi in bracket 1 minus minus 1 raised to n into sine n omega t. So now if I am to write this in terms of a series, I will get x of t as, for n equal to 1 it will start because n is odd, so it is 4a upon pi into sine omega t because n equal to 1. Next term I will get if I put n equal to 3, a next odd number, and that is 4a upon 3 pi into sine 3 omega t likewise. So finally I can write this as x of t is equal to 4a divided by pi in bracket sine omega t plus sine 3 omega t divided by 3 plus sine 5 omega t divided by 5 and so on. So this will be the final answer we will be getting. Over here, this term is a fundamental component because that I'll get after putting n equal to 1, and remaining are nothing but the harmonics. So just to observation, over here I can say a fundamental component will be present with odd harmonics. So this is nothing but a trigonometric form of a Fourier series of x of t. Thank you.